Effectively grounded means a power system where a fault on any phase creates a fault current large enough to activate protective devices within a specific time, usually 0.5 to 1.0 seconds. This involves connecting the neutral point to ground through a resistor or impedance. Solidly grounded means a power system where the neutral point is directly connected to ground without intentional impedance. This offers a very low impedance path for fault currents, reducing the fault duration and severity. Zero sequence reactance, symbolized as C subscript 0, is the reactance an electrical system presents to zero sequence currents. These are unbalanced currents flowing in three conductors, summing to zero, often due to ground faults. In a three-phase power system, the symmetrical components method analyzes currents and voltages. It breaks down unbalanced three-phase quantities into three balanced sets of components: firstly, zero sequence; secondly, positive sequence; and thirdly, negative sequence. Zero sequence components have the same direction and magnitude in all three phases. They facilitate the flow of zero sequence currents, which travel in all three conductors and sum to zero. Positive sequence components have the same magnitude and direction in all three phases, but they are phase shifted by 120 degrees. They represent normal three-phase power flow. Negative sequence components have the same magnitude but opposite direction in two of the phases, with zero magnitude in the third phase. They can arise from unbalanced loads or faults. Zero sequence reactance is primarily determined by the system grounding method, while positive and negative sequence reactances are influenced by the system impedance and the fault location. Understanding these concepts is critical for protecting power systems from faults and ensuring reliable operation. Properly grounded systems limit overvoltages during ground faults, reducing the risk of equipment damage and improving safety. The symmetrical components method allows engineers to analyze unbalanced fault conditions and design effective protection schemes. The magnitude of the zero sequence reactance impacts the ground fault current level. Lower values result in higher fault currents, potentially enabling faster clearing times but also requiring more robust equipment. Conversely, higher zero sequence reactance values limit fault currents, potentially reducing stress on equipment but possibly delaying fault clearing. In solidly grounded systems, the zero sequence reactance is minimized, leading to high fault currents and rapid fault clearing. This helps limit the duration of overvoltages and reduces the risk of transient instability. However, high fault currents can also cause significant stress on equipment and require careful coordination of protective devices. Effectively grounded systems use impedance to limit ground fault currents to a more manageable level. This provides a balance between fast fault clearing and reduced equipment stress. The choice of impedance value depends on various factors, including system voltage, fault current capacity, and coordination requirements. The positive sequence reactance is an important parameter for determining the system's short-circuit capacity. It represents the impedance to balance three-phase currents and affects the magnitude of fault currents during symmetrical faults. The negative sequence reactance is important for analyzing unbalanced faults, such as single line-to-ground faults and line-to-line faults. It affects the distribution of fault currents and voltages in the system. Zero sequence impedance plays a significant role in ground fault protection, in particular the ground fault currents path. Knowledge about zero sequence impedance helps to set ground fault protection relays properly. Zero sequence impedance is determined by factors such as transformer connections, grounding methods, and the presence of dedicated ground conductors. For example, a delta-Y transformer connection provides a path for zero sequence currents to flow, while a delta-delta transformer connection does not. Similarly, a solidly grounded system has a low zero sequence impedance, while a high resistance grounded system has a high zero sequence impedance. The choice of grounding method affects the magnitude of ground fault currents and the sensitivity of ground fault protection. Solidly grounded systems provide the highest level of ground fault protection, but may also result in higher fault currents and increased equipment stress. High resistance grounded systems limit ground fault currents but may require more sensitive ground fault relays. It's important to consider system characteristics and protection objectives when selecting a grounding method. Zero-sequence components arise in systems with unbalanced loads, faults, or asymmetrical configurations. Unlike positive and negative sequence components, which represent balanced operating conditions or symmetrical disturbances, zero-sequence components reflect imbalances within the power system. The magnitude and phase angle of zero-sequence currents and voltages provide valuable information about the type and location of faults. Protective relays use this information to detect and isolate faults quickly. Understanding the behavior of zero-sequence components is essential for designing effective protection schemes. In summary, the symmetrical components method provides a powerful tool for analyzing unbalanced conditions in three-phase power systems. By decomposing unbalanced quantities into balanced sets of components, engineers can simplify the analysis of faults and design effective protection schemes. Effectively grounded systems offer a balance between fast fault clearing and reduced equipment stress, while solidly grounded systems prioritize fast fault clearing but may result in higher equipment stress.